second video in Chapter 2, so we're going to start off with this histogram. This histogram represents the final grades for Mr. E's calculus class. So we have a histogram over here, and you can see it says final grades. As soon as the screen comes back, you can see it says final grades going across the bottom, and then you can see the different counts. So you can see that one student scored between a 50 and a 55, and two students scored between a 55 and a 60, and 5 students, you might want to write these on your paper too, scored between a 60 and a 65. 6 students got between 65 and 70. 11 students in the 70 to 75 range. 10 got scores there. 7 got scores there. 4 got scores there. 3 there. And 1 there. For a total of, if I add them all up, 4, 8, 15, 25, 36, 42, 47, 50 total students. So the question is, what proportion of this curve lies below 70? So you would take a look and you would go from 70 on down. So that proportion then would be 6 and 5 is 11, 12, 14 out of 50. Alright, so 14 out of 50, which is 28%. What proportion of the curve is between 70 and 75? That would be this group right here. So that's 11 out of 50. And that equals 22%. Now, if the proportions represented by each bar in the histogram were equal to the area of each bar, then what's the total area under the curve? Now, by the curve, when I talk about the curve, what I'm talking about is, let's imagine we connect the dots in the center of each bar. So if we were to connect these dots, we would make a nice curve that looks something like that. So you would say then, here's 70. You would estimate that from 70 down would be these four bars, which we just did a minute ago and we said was 28%. And between 70 and 75 would be this bar, which we did a minute ago and we said was 22%. If the proportions represented by each bar were equal to the area under the bar, so this proportion was 1 out of 50, this was 2 out of 50, this was 5 out of 50, and so on. If each bar represents the area, what would you get if you were to add up all the area under the curve? Well, hopefully you recognize that if we were to add up the area of each bar, which was representing the area underneath the curve, that would add up to 100%. Alright, so the area under the curve represents the area of the bars, and the bars add up to 100%, therefore the area under the curve also adds up to 100%. And that's a key distinguishing feature of density curves, which is what we're going to get into next. Now, as far as what is a density curve, in Chapter 1 we developed a kit of graphical and numerical tools for describing distributions. So now we're going to add one more step. We're going to talk about exploring quantitative data. First, always plot your data, make a graph. Right? Remember that from Chapter 1. We talked about a lot of different types of graph, but it's always a good idea to look at a graph. Secondly, when you're describing a distribution, you want to talk about the shape, the center, the spread, and anything unusual you want to cuss. And then number 3, create a numerical summary to briefly describe center and spread. So the mean for the center and the standard deviation for the spread. This is what we learned in Chapter 1. Now we're going to add another step. Sometimes the overall pattern of a large number of observations is so regular that we can describe it by a smooth curve. And this happens very, very frequently, so you want to be aware of it. So that leads us then to a definition of a density curve. A density curve is a curve which represents an idealized distribution, so a perfect distribution. Idealized means a perfect distribution. It is always characteristics of a density curve. It is always on or above the horizontal axis. It will have an area of exactly 1 or 100% underneath it. A density curve, we use them to describe the overall pattern of a distribution. And finally, the area under the curve and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval. Like we did on the previous slide with the histograms, the area under the curve and above any interval of values on the horizontal, so for example, the area under the curve less than 75, that would be everything less than 75. It is the proportion of the observations, the percentage, the 14 out of 50 or the 11 out of 50 that we saw on the previous slide, that fall in that interval. That's what the area of the curve is. I thought this cartoon was pretty cute. I'll give you a minute to read it. It has to do with density curves. I thought that was cute, so hopefully you did too. Gives you a little sense of a statistician's sense of humor there. So when you're describing a density curve, the measures of center and spread apply to density curves as well as to actual observations. And by measures of center and spread, we're talking about the mean and the median. And for spread, we're talking about standard deviation and IQR and the range. So distinguishing the median and the mean of a density curve. First, the median of a density curve is the equal areas point. It's the point that divides the area under the curve in half. Alright, so the median is the equal areas. The median is the balance point, the point at which the curve would balance if it was made of solid material. So that third picture down there represents the mean because it's balancing. The median and the mean are the same for a symmetric density curve. They will both lie at the center of the curve. Remember that the mean of a skewed curve is pulled away from the median in the direction of the tail. So the mean gets pulled towards the tail. The median doesn't change because the median is resistant. But the mean is not resistant, so the mean gets pulled towards the tail. So you have to remember that. So here's an example that you should draw these pictures. When a density curve is symmetric, the mean and the median will be the same. They will be in the exact same spot, and you can see a nice symmetric picture of a curve there. When the curve is skewed to the right, the mean lies to the right of the median. So here you see a picture of a curve that's skewed to the right. The mean is pulled in the direction of the skew, therefore the mean gets pulled to the right. And then you could also draw a picture of a skewed left and see where the mean gets pulled to the left. So here are some basic symbols that we're going to be using throughout the rest of the course. Mu and sigma to distinguish the mean and standard deviation of density curves from those of actual observations, because remember, mu and sigma are idealized population parameters. We don't actually know them most of the time because we don't actually know the whole population. So we use mu and sigma when we're talking about populations, when we're talking about density curves. Mu is the mean and sigma is the standard deviation. When we're talking about sample data, concrete data that we've actually gathered and we're manipulating, we're doing something with in our calculators, we're talking about sample data in that case, we use x bar to represent the mean, and we use s, or s of x, to represent the standard deviation. Okay, I told you this was a nice short one.
That's all, folks.
So, hopefully you have all those notes and you're ready to go for tomorrow. So I'll see you then.